All right, here we are at the acceptance test for the Ling LS-100 shaker. In front of us, what you can see is the shaker without the cover. Cover is in the back, and I have that off to go around and highlight some of the items inside or under the shaker. Over here, what you'll see is the upper and lower limit. This micro switch, if it's plucked up or low, means that the shaker armature is being exercised outside of its limits. Depending upon what amplifier you have, you may have or may not have a set of contacts that will disable the output to the shaker to protect it. If you do not have that feature on your amplifier, then what I suggest you do is take the output of the amplifier and put it through a relay and have the relay control operated by the output by this connection here of these micro switches. Okay, around here is all of your flexures. Okay, and you can see there's actually a fuse that's on the amplifier output, which connects to the armature windings to protect it. You have the DC cable, which is 4 conductors. 2 of them are the armature connections, one being the red wire, and then I'll show you the black one as we move around. There's also 2 wires, green wires, that connect to the upper and lower limit, and this is your blower connection or vacuum blower that will provide airflow if you intend to use this for extended periods of time, long testing. You may want to consider a small blower on that, which will actually take the ambient air through the vents in the shaker head cover and pull ambient air down across the shaker so that it cools, okay, and keeps it from overheating. On top of this, we have an accelerometer, and that happens to be one that I have in stock. It's a Dytran. You can see the model number, and it's 9.54 millivolts per G, which is the actual sensitivity on that particular unit. And you can get different ones, but this seems to be a pretty good range for operating vibration testing. That's the black wire that comes off the cable, and that is directly in there. Now, one of the things that you'll also have to verify is that you have the polarity right, depending upon your amplifier connection. So what you're going to want to do is take your amplifier, and hopefully your amplifier can put out a steady DC voltage, either plus or minus. If you put plus on one of the wires, then if it goes in the upper direction, that should be correct. If you go flip it around and change the polarity, you go minus, you go negative. Okay, that would be your negative side. So this way your controller or your signal source will be in phase with the armature direction. It's pretty simple. You can use a 9-volt battery with a little clip and just connect it across the black and the white wire in the cable. As you can see here, there's the black and the white, and then there's the 2 greens, which are the control signals or the limit control. All right, moving along. I'm using the VR 9500 controller. Below is the 4-channel, and obviously we're only using one of them. And I have a small LDS PA 25 amplifier. Moving around the back, my notebook PC, or my not my notebook, but my PC, my notebook PC does not have an Ethernet port, so I have to use a dongle converter because my controller output is Ethernet. So that's what the blue wire is, and it goes to the back of the controller. There's the AC line to the controller. The yellow cord on the BNC there is the drive signal coming out of the controller, and it goes into the amplifier right there, and that's the shaker signal input. The output comes off the red and black wire, and as you can see, the two green are not connected to anything right now because this shaker does not support that. That's the signals that you would put to control a relay, and put a little relay in line with those, with the amplifier output. That's pretty much the setup. And what I'm going to do first is we're going to go ahead and I'm going to turn the gain up a little bit, reset the unit, and I'm going to open up my software. And the first thing I'm going to do is run what's called a system check. Okay, and what system check is going to do is going to test the system to make sure that I have complete control of the system. But before I do that, I want to show you that with this particular controller, and many of them, there are system limits. The system limits, okay, for the shaker, for the as you can see, the Ling LS-100, it's 100 force-pounds. The velocity peak is 100. The displacement peak is 0.75, so it's 3/4 of an inch peak to peak. Peak to peak, 3/4 of an inch. It's got some of the information relating to the actual shaker, so that the controller does not overdrive and destroy the shaker. One of the other important things is that I have the right sensitivity selected here, and what you can see is I have channel 1, which is my input channel. That's this guy right here. Okay, the input channel, and I have 10 millivolts per G selected. Realistically, I would change that to the actual sensor calibrated measurement, which is 9.54, but again, for this test, it's not really critical. But we do have 10 millivolts per G. If I had 100 millivolts per G, obviously there'd be some issues because the controller would not see the response back from the shaker that it expected, and you would abort. All right, moving right along here. Okay, what I'm going to do is start this little test. It's basically going to put out a 30 hertz frequency. It's going to put about 4.6 Gs to develop that, and we're going to have a 0.1 inch displacement. As you can see, the sine wave is coming up, and once it comes up to full power, the yellow arrow will turn green. Okay, it's green, that means it has control. Now the important thing here is to look at this waveform. This is the waveform coming back from the accelerometer that is connected, and you may or may not be able to see this on this camera. Yes, you can see probably a little bit of a blur there. Okay, that's the 0.1 inch peak to peak movement of that armature that's blurring the top of it. And I'll try to steady it a little bit. So you can see the blur on the upper and lower end of the armature, which is actually what's going on. A couple things. One is when you do testing, you want to put an anchor point and a service loop, because you don't really want this cable flapping around here and banging up and inducing more noise into the system. Okay, so what we're running here is the 30 hertz signal coming from the black and white wire here into the armature. The armature current and voltage relationship is interacting with the permanent magnet here and causing the armature to spin, to bounce up and down because of its flexures. Obviously, if it was on bearings, it would spin like a motor would. All right, now the signal coming back from that is recorded by the accelerometer, and again, you can see the vibration there, and I'll show you if I stop it, okay, what will happen, and then I'm going to resume it again. Okay, you can see how it cleared up. I'm going to start it back up again, and once it comes up to power, you'll see it. Now there is what's called an optical wedge that you can put on there, and what it does is it actually will give you a visual monitor. Now you can see it's coming up to the full power. It is, and again you can see it blurring, and you can actually measure that displacement, okay, with an optical wedge. All right, now we're up here and let's take a look at the actual response back. As you can see, we have a nice clean response, and I'm going to induce some noises, but just by tapping on this, and you can see that this thing is really working. Okay. Okay, that's me. What I'm doing is I'm just tacking on the side of it, and you'll see that random noise. Okay, so now I stopped tacking, it got cleaned up, okay, and what that's indicating is that the armature suspension system, all the guidance and bearing systems on this shaker are really very much as they should be, okay, near perfect. If there was a problem with the armature, the bearing, or one of the suspension flexures, you would get the tapping and ringing, okay, because of the imbalance or the resonance coming off of any one of those items I just mentioned. Okay, next thing I'm going to do is I'm going to stop the test, okay, and I have what's called a sine sweep, and I'm going to load that, and what this is going to do is going to take a base frequency of 20 hertz out to up to 3,000 hertz at 1 G. And again, this is going to be sort of a benchmark to evaluate the status of the system. I'm going to press start, and as you can see, my ending frequency is 2,000. I'm getting a little shadow here, and I've got a demand of 1. It's based on G's, and I'm going to do a 1 G test on that, and I'm going to start that up by starting the test. This is asking me if I want to create a file. This controller does that, and I'm going to say no. It's going to say if I wanted the output in a directory and store the information. I'm going to say no. And what's going to happen is this thing is going to start to climb up here, and once it gets to 20 hertz, it starts going tracking. You can see the arrow going up a little bit. We can see the shaker starting to move. Hard to do, but yeah, you can see it there starting to move and get a little response. We're going to go back to here, and we're at green, so it's up to power. It's up in the test parameters that we selected, and it is moving right along. This is going to take a little while. If you have good ears, you may be able to hear it. The drive output signal on the bottom is a curve, is the output drive voltage, and as the frequency range is being driven up, the power curve is generated, and obviously at lower frequencies you require more power, and you can see it's starting to come up now. The frequency now is, I'm sorry about that glare there off the bulb or whatever, but let me see if I can change this a little bit. I'm not sure if that did anything. Okay, you can see the frequency now is moving up. You may start to hear it. Maybe if I turn this. Okay, but what she's doing, she's driving through the range. We're at 1,000 hertz now, 1,000 hertz and climbing. You can hear it whistling, obviously. And we're not going to see much because the displacement is pretty low. But the important thing here again is the profile of what you're seeing. If there were problems, resonance in the armature, you'd start to see really, really big spikes. You're going to see, it's not going to be flat line with anything because we're talking about dynamic system, and it's going to basically have a little bit of issues, but that's negligible and quite in spec. What you can see now, the test has ended, and I'm going to try to get in there. Actually, let me just put this down a second and see if I can turn that overhead light off. It's really annoying me. Hold on. Okay. Let's see if that's any better. No, I don't know where that's coming from. Okay, but what we can see is, I'll get in here close, and you can see basically that's pretty much flat line. What this is showing is the actual signal. There's a blue and a green control and demand line. The dotted line is the first set of limits, sort of like the bands where there's some possibly issues or could cause some problems. The red are the abort, so if any signal went up into the red area, it would automatically stop the system, and again, not to damage the device or the system with too much resonance, frequencies, or energy being coming into play. All right, the next test we're going to run is what's called an 810G. This is a normal mill spec, and it's a profile that's used for testing devices. It's sort of you can see the profile there. It's pretty intense as far as testing. It's going to generate almost 2 G's of force. And what's going to happen, I'm going to press the start button now, and this again is asking me if I want to create start over. Do I want to create anything? No. Do I want to create anything? No. Okay, and what's going to happen now is it's going to come up into this particular controller. Like most of them, they start to iterate the controller and get the signal coming up little by little and bring it under control. You can see it's moving along here nicely. And the profile is in profile, in its spec range, in its GRMS range. That's in the spec. And again, I have no idea where that's coming from. And you can see we're in that profile, and it's just marching along, doing what it's supposed to do. You can see the drive signal below obviously varies and changes with each directional change and power change. Again, this is a random test, running approximately 1.4 G's, and you can just watch the system run here a bit. I'm going to just tune in a little bit on the pointer, okay, which has to do with the upper and lower limits, and you can see it's bouncing well within the upper and lower limits, showing its displacement. And you can hear it's very quiet, no rattles. Okay, that pretty much concludes the testing of this system. We have done much more intense testing, but for the visual now and the amount of allocated time that we have on YouTube to post this, this pretty much completes the testing of the LS-100. And I'm just gonna spin this around a little bit, and we'll go right in here. Serial number. Okay. All right, this concludes the test.